Welcome back to The Explainer. Today, we are unpacking something absolutely massive. We're talking about a concept that could literally change the world: artificial photosynthesis. Imagine for a second if we could just mimic the way everyday leaves generate energy from the sun, but engineer it specifically to solve our global energy crisis. Well, that is exactly what researchers are doing right now. And let me tell you, the scale they are working at is just mind-boggling. But before we get into the how of it all, I want you to just take a look at this number. 5%. Yep, just 5%. That is the shockingly low percentage of solar radiation that one of our most promising, stable materials can actually absorb right now. Imagine having this massive, practically limitless solar resource beating down on us, and we're letting 95% of it just slip right through our fingers. Fixing that is the major hurdle this research is trying to conquer. So here's our roadmap for today. First, we'll look at the promise of solar fuels. Second, the sunlight bottleneck. Third, a nanoscale solution. Fourth, we'll go inside the two modules. And finally, seeing the microscopic results. We've got a very clear path from the macro problem to a microscopic solution. So let's get right into it.
Section 1. The promise of solar fuels mimicking leaves to save the planet. Okay, let's dive into this grand vision. The research we're exploring today comes to us from scientists Juan Ernesto Neri Cruz and Hector A. Calderón, down at the Instituto Politécnico Nacional in Mexico. And their work? It focuses on the ultimate goals of artificial photosynthesis, or AP devices. Basically, the main goal here is to drive solar energy directly into chemical bonds. Now, we aren't just talking about generating electricity for the power grid, we're talking about synthesizing a tangible, easy-to-handle liquid fuel. And the real brilliance of this idea is the dual-action environmental benefit. To actually create this liquid fuel, these devices actively pull carbon dioxide right out of the environment, directly reducing CO2 emissions. It is literally the dream of creating clean fuel from thin air and sunlight.
Section 2. The sunlight bottleneck. The problem with TiO2. So what is exactly standing in our way?
To really understand the major chemical roadblock in this clean energy dream, we have to talk about titanium dioxide, or TiO2 for short. It's a completely non-toxic, chemically stable semiconductor that's widely used for photocatalytic applications. And in plain English, that just means it uses light to kickstart chemical reactions. The scientific community leans heavily on this stuff because it doesn't break down easily during those reactions and, it's super safe to use. Fundamentally, it is kind of the perfect canvas for a catalytic reaction.
And this brilliantly illustrates the massive plot twist. Standard titanium dioxide only absorbs light in the UV range. And UV light, that accounts for a mere 5% of the solar spectrum. So yeah, an enormous 95% of the sun's radiation hitting it is just completely wasted. It is literally like trying to fill a giant swimming pool with a leaky eyedropper. Obviously, if we want artificial photosynthesis to actually work on a global scale, we absolutely have to fix this massive inefficiency. Which brings us to Section 3, a nanoscale solution, engineering at the atomic level.
To solve this huge macro-scale energy crisis, Neri Cruz and Calderón realized they had to go small, like atomic-level small. What we're looking at here is the blueprint for a heterostructured nanowire array. Essentially, they're taking different materials and layering them together to form a microscopic energy factory. They kick things off with an aluminum mask, which is packed with these highly ordered, incredibly tiny cylindrical channels. How tiny? The pores have an average size of just 46 nanometers. To put that into perspective for you, a single human hair is roughly 80,000 to 100,000 nanometers wide. So we are talking unbelievably small. They use this tiny mask to synthesize a perfectly structured two-dimensional array of nanowires. But here's the thing, just manufacturing the nanowires isn't going to cut it. They need to completely alter the chemistry to capture more radiation. First, they dope the titanium dioxide with a metal ion, specifically cobalt, to adjust its behavior. Second, and this is the really cool part, they embed these nanowires with noble metal gold plasmonic nanoparticles to be exact. Now think of these plasmonic particles as tiny, highly tuned antennas designed specifically for capturing light. Adding them into the mix vastly improves how much solar radiation is captured, mainly by boosting how efficiently the system separates and transfers electrical charges. In physics, we call these electron hole pairs. It's a real game changer for sure. Let's move on to Section 4, inside the two modules, creating fuel from thin air. Let's see how this array actually functions inside the device.
All right, so we have our highly engineered, gold-embedded nanowires ready to soak up the sun. But how do they actually function? Well, the researchers describe the device as being built in two distinct modules, with each one utilizing this nanowire nanoparticle array. So the crucial point is how these two steps interact seamlessly together. Step 1 happens in the first module. Here, the captured solar energy is used to drive water splitting. It literally breaks water down to obtain hydrogen ions. Then we move to step 2. The second module takes those newly freed hydrogen ions and combines them with CO2 from the surrounding environment to synthesize our final fuel. Honestly, it's just an incredibly elegant closed-loop chemical dance.
Section 5. Seeing the microscopic results. Proof in the pictures. We are about to look at actual microscopic imagery from the researchers' lab, and it is stunning.
Because in science, right, theory and 3D renderings are really only half the battle. You have to prove you actually built what you designed. Just look at the sheer scale we are observing here in these actual images from the lab. Now, what's really interesting about this slide is if you look on the left at the scanning electron microscope image, you're seeing the actual detached nanowire array they synthesized. The arrows point to a wire diameter of just 63 nanometers. Then, I want you to guide your eyes over to the high-resolution image on the right. If you look really closely inside that tiny black box and at the zoomed-in inset in the bottom right corner, you can clearly see those embedded gold nanoparticles. And get this, these particles have been measured at an astonishing 4 nanometers in size. They successfully embedded impossibly tiny gold fragments right into the nanostructure of the titanium dioxide exactly as they planned.
It is an absolute triumph of material science. It proves that we can take a highly stable, but, let's face it, pretty inefficient material and turn it into a solar-absorbing powerhouse that can literally turn sunlight, water, and CO2 into usable fuel. Which brings us to our final thought for this explainer. I want you to really think about the global implications of this. If meticulously engineering something as impossibly tiny as 4 nanometer gold particles can unlock the door to solving our macro-level energy crisis, what else is hiding at the microscopic level, just waiting for us to discover it? Thank you so much for joining me for this explainer. Until next time, keep looking closer.